Hey everyone, welcome back to the channel. Today, we're diving deep into one of the most powerful techniques in natural language processing, text classification. Whether you're scrolling through your inbox, reading news articles, or shopping online, text classification is working behind the scenes. By the end of this video, you'll understand exactly how it works, the different algorithms you can use, and how to implement them yourself. If you're new here, we break down complex AI concepts into simple, actionable tutorials. So hit that subscribe button and let's get started. So, what exactly is text classification? Simply put, text classification is the process of assigning predefined categories or labels to text documents. It's a supervised learning task, which means we train a model on labeled examples, and then it can predict labels for new, unseen text. Think about it this way. When you receive an email, your inbox automatically sorts it into primary, social, or spam. That's text classification in action. The input is always text. Could be a sentence, a paragraph, or an entire document. The output is a category label like positive or negative, sports or politics, urgent or not urgent. Here's the key difference from other NLP tasks. We're not generating new text or translating languages. We're simply putting text into buckets based on its content. Now let's break down the workflow. Text classification happens in 4 main stages. Stage 1. Data collection. You need labeled training data. Texts with their correct categories already assigned. The more quality data you have, the better your model will perform. Stage 2. Preprocessing. Raw text is messy. We clean it up by converting to lowercase, removing punctuation, eliminating stop words like the and is, and often applying stemming or lemmatization to reduce words to their root forms. Here's what preprocessing looks like in Python. Notice how we're transforming running to run and removing all the noise. Stage 3. Feature extraction. Computers don't understand words. They understand numbers. So we convert text into numerical features using techniques like bag of words, TF-IDF, or modern word embeddings. TF-IDF is particularly clever. It gives higher weights to words that are important in a document, but rare across all documents. So the word the gets a low score, but quantum in a physics article gets a high score. Stage 4. Model training and prediction. We feed these numerical features into a machine learning algorithm. It learns patterns, and then it can classify new texts. All right, now for the fun part. Let's explore 3 powerful classifiers you can use, starting simple and building up to state-of-the-art. Naive Bayes. First up, Naive Bayes. Don't let the name fool you. This naive algorithm is surprisingly effective. Naive Bayes is based on Bayes' theorem from probability theory. It calculates the probability of each class given the words in your document and picks the class with the highest probability. It's called naive because it assumes all features are independent, meaning the presence of one word doesn't affect the presence of another. In reality, that's not true, but the algorithm still works great. Let's see it in action with scikit-learn. This is remarkably simple code, just a few lines to train a spam classifier. We're using count vectorizer for feature extraction, training on our data, and boom, predictions. It's that straightforward. So when should you use Naive Bayes? It's incredibly fast, works great with small datasets, and is easy to interpret. The cons? It assumes feature independence, which isn't realistic, and it can struggle with complex patterns or relationships between words. Pro tip: Naive Bayes is perfect for your first prototype or when you need real-time classification. Logistic regression. Next, logistic regression. Despite the name, This is actually a classification algorithm, not regression. Logistic regression uses a sigmoid function to squash predictions between 0 and 1, giving you probabilities for each class. It learns weights for each feature to make optimal predictions. The implementation is just as clean as naive Bayes. We're using TF-IDF here instead of simple counts, which often gives better results. Notice the max iter parameter. That's how many iterations the algorithm takes to converge. Sometimes you need to increase this for complex datasets. Logistic regression is more robust than naive Bayes, handles correlated features better, and gives you probability scores. It's also very interpretable. You can see which words influence each class. The downsides? It requires more data to perform well, and it's linear, so it can't capture complex nonlinear patterns without feature engineering. Use logistic regression when you need reliable performance and interpretability without the complexity of deep learning. Fine-Tuned BERT. And now the heavyweight champion, Fine-Tuned BERT. BERT stands for Bidirectional Encoder Representations from Transformers. This is a deep learning model pre-trained on massive amounts of text, understanding context in both directions. Unlike the previous methods that see words as independent features, BERT understands that bank means something different in riverbank versus savings bank. Here's how we fine-tune BERT using Hugging Face transformers. This is more involved, but the power is worth it. We load a pre-trained model, tokenize our text using BERT's special tokenizer, and fine-tune on our specific task. The trainer API handles all the complexity for us. The pros? State-of-the-art accuracy, deep contextual understanding, and it excels with complex language. BERT can understand sarcasm, nuance, and context that simpler models miss. The cons? It's computationally expensive. You'll want a GPU. It requires more training data to fine-tune effectively, and it's a black box, making it hard to interpret why it made a decision. Use BERT when accuracy is paramount and you have the computational resources. Let's see where text classification is making a real impact in the world today. Spam filtering. First, spam filtering, probably the most well-known application. Gmail processes millions of emails per second, automatically detecting spam with over 99% accuracy. The classifier looks at patterns, suspicious links, common spam phrases, sender reputation. It's constantly learning from user feedback when you mark something as spam. News categorization. News categorization powers every major news website. Articles are automatically tagged as politics, technologies, sports, etc., making it easy for readers to find content they care about. Google News uses sophisticated classifiers to organize content from thousands of sources in real time. Review classification and sentiment analysis of reviews. This is huge for businesses. Amazon, Yelp, TripAdvisor, they all use text classification to identify positive and negative reviews, flag fake reviews, and surface the most helpful comments. Companies use this to monitor brand reputation, understand customer pain points, and improve products based on feedback. So with all these options, how do you choose the right classifier? Here's my framework. Start with your constraints. Small dataset and need speed? Go with naive Bayes. It'll give you a solid baseline in minutes. Medium dataset and need reliability? Logistic regression with TF-IDF. It's your sweet spot. Great balance of performance and interpretability. Large dataset and need maximum accuracy? Fine-tune BERT, but make sure you have the GPU resources and training time. Now let's talk tuning. These strategies will boost any model's performance. 1. Cross-validation. Never trust a single train test split. Use k-fold cross-validation to get reliable performance estimates. 2. Hyperparameter tuning. Use grid search CV or randomized search CV to find optimal parameters. For naive Bayes, try different smoothing parameters. For logistic regression, tune the regularization strength. For BERT, experiment with learning rates and batch sizes. 3. Handle class imbalance. If you have way more examples of one class, use techniques like SMOT, class weights, or stratified sampling. 4. Look beyond accuracy. Use precision, recall, and F1 scores. A confusion matrix will show you exactly where your model is making mistakes. 5. Ensemble methods. Combine multiple classifiers. A naive Bayes plus logistic regression ensemble often outperforms either. And there you have it, a complete guide to text classification. We covered what text classification is, how the pipeline works, 3 powerful classifiers with code examples, real-world applications, and strategies for choosing and tuning models. If you found this helpful, smash that like button, subscribe for more AI tutorials, and I'll see you in the next video. Happy coding!